So I'll be having my first actual office hour, during my office hour this afternoon. So I'll hang out in my office there. If there's enough people who move to a bigger room, so maybe I'll be there at 4 o'clock. All right. So we are talking about a very important problem we're doing for many, learning for something new for others. That's for that spoon where I was wondering. Yeah, you know I washed that spoon. Anyway, I might have it in my yogurt this morning. It's like, what did I do with that spoon? All right. Happy Monday. Right, yeah. So, we're talking about two-level systems. Particularly, we're talking about the two-level atom, one of the most important systems in thinking about in quantum optics and in all of, I would say, quantum information science, the qubit. When we talk about qubits, much of the way in which we think about a quantum bit rests upon physics understanding of spin and momentum. So those poor computer scientists who work on quantum information have to learn something about spin, and so do we, remind ourselves. Just to remind you just a few of the foundational facts. So our star of our show are the so-called Pauli operators, and they satisfy a bunch of algebraic relations that you should be having at your fingertips, if you don't already. And that's really very, very important. So we'll be practicing lots with that. And I encourage you, if it's not so fresh for you, to review that in whatever course you learn this material. Right, so we often talk about the Pauli matrices, and when we do that, we are thinking about the representation of these operators with respect to the standard basis. And often these are called X, Y, and Z, but I don't do that. We'll call them sigma X, sigma Y, and sigma Z. Right, so some important properties that we discussed, and just to again emphasize them. These, of course, are Hermitian matrices, the Pauli matrices, and their eigenvalues are plus and minus 1 for any of them, X, Y, or Z. They're all similar matrices. They're just rotations of one another, therefore they must have the same spectrum. And what must be true is the matrix along any direction, and what that is that this is a superposition of the matrix sigma X, sigma Y, and sigma Z, depending on components of this. So this is some matrix itself in whatever basis representation you choose. And this matrix is similar to sigma Z, and thus also has the eigenvalues plus 1 and minus 1. Okay? And therefore, these matrices are traceless. Their sum of their eigenvalues is the trace of the matrix, and that sum is 0. And moreover, these matrices all square to the identity. Okay? These are all very important properties that we use all the time. Moreover, these matrices, together with the identity, which is sometimes called sigma 0, are a set of linearly independent matrices in the space of matrices. So the matrices themselves can be thought of as vectors. Okay? A vector space of matrices. We can take superpositions of matrices, therefore it's a vector space. And moreover, we can put an inner product on that space through the so-called Hilbert-Schmidt norm, or the Euclidean course, this case, this dagger is irrelevant, so I don't really need to put it there, but I did just so I can erase it. And these are trace orthogonal, okay? They're not normalized, they're just what they are, right? So that factor of 2 is there, because the sum of the eigenvalues for the identity is 2. And thus, we can express any 2x2 matrix or an operator on a 2D Hilbert space as a linear combination of the identity matrix and the 3 Paulis, with written here with parameterization so that A0 is the trace of the matrix, and this vector of coefficients A are the vector of coefficients associated with the trace overlap of A with each of the Paulis. So there will be an A sub x, which is sigma x with this. There's an A sub y, which is sigma y with that. Okay, so there are 3 numbers that represent the 3 coefficients that go here. This is a very important formula. We use it all the time. And one thing that this formula allows us to do is to instantly read off the eigenvalues and eigenvectors of any 2x2 matrix. So forever and a day, you will never again write down the characteristic equation of a 2x2 matrix and diagonalize it by solving the quadratic formula. You will not do that anymore. What you will do is re-express your matrix as a superposition of Paulis and then just look at the answer. And the answer is this. There is one eigenvalue that I'm labeling A sub plus, which is A0 plus the magnitude. So this is the square root of AX squared plus AY squared plus AZ squared. That's the magnitude of that, where this is a vector that has 3 components, AX, AY, and AZ. And that's the magnitude of that vector. And then the other eigenvalue is A0 minus that, over 2. Okay? And the eigenvectors of this matrix then correspond to spin up along the direction of A and spin down along the direction of A. Let me clarify that a little bit. So, I can write this matrix I've expressed this vector as having a magnitude and a direction. Okay? This, as we wrote up here somewhere, is the Pauli matrix along the direction A. Okay? That's what that means. Thus, the eigenvectors of this operator are the eigenvectors of this operator. Because everything is an eigenvector of the identity. I can give a patootie about that. I only care about whether what is the eigenvector of this. And that's automatically eigenvector. And the eigenvectors of this are spin up and spin down along whatever that direction is. So, the algorithm in our heads, forever to be used for how you diagonalize a 2x2 matrix is you first find this vector, well, you have to find the trace, and you find that vector. You find that vector by looking at the trace overlap with that, which you will be able to do by eye after a little practice. And then you just look at its magnitude and direction, and you're done. And it's maybe not a simpler algorithm than doing the the characteristic equation with the quadratic equation, but it's a physical thing that you will be able to use all the time because this has geometric meaning. All right? And let us remind ourselves of that geometry, because that's what we were talking about last time, and we want to zoom through this. So, importantly, angular momentum is the generator of rotations of a vector. So, geometrically, if we think about rotations in R3, we think about a vector whereby we have some axis, I'll call it E sub A, the axis of rotation, and we're going to rotate a vector V around that axis by some angle theta. Okay? So that is a geometric rotation according to the right-hand rule. It takes the vector V to the vector V prime. So there is some rotation operator that takes V to V prime in 3 space. Okay? Now, in quantum mechanics, that is implemented by a unitary transformation. We have a rotation operator I'll call it D, that rotates the vector about an angle A by the around the axis A by the angle theta, which is equal to e to the minus I theta, the component of angular momentum, which I'll generically call J in units of h bar. So that's the rotation operator for an arbitrary angular momentum J that rotates around that axis by that angle in the same manner. Okay? And this forms the unitary transformation. If I looked at, for example, the position vector or any vector operator, then this is E prime. So this unitary transformation performs this rotation. This is an operator on Hilbert space. This is a vector operator, right? Very good. So for example, if I had a rotation that took a unit vector along some direction to some other direction, then I can look at how the components of some vector, like the components of the Pauli vector, operate, and that's a passive rotation. And so it goes, you may remember, if you want to rotate the coordinates, you rotate backwards, right? The passive versus, it's always confusing, the passive rotations versus the active rotations. Right? So a passive rotation rotates the coordinates, goes with the other direction. Too many decorations. So that's a rotation on the coordinate rather than on the vector. Very good. For example, let's say, so let me say this slightly differently, because I want to specialize to the specific case of a rotation that takes the z-axis to some arbitrary direction on the sphere. So I'm looking at that particular rotation. Okay? So for that case, so now what I claim is, if there is such a rotation that takes the z direction to some direction on the sphere, I'm trying to possibly draw that. Here's the sphere. Here's some direction on the sphere. Here's the z-axis. This can be expressed in terms of, say, having some, here's the y-axis, here's the x-axis, this thing has some projection in the xy plane, it has an angle phi with respect to the x-axis, and angle theta with respect to the z-axis in the usual spherical polar coordinates, right? So, firstly, I claim that if I take the vector that's spin up along z, and I apply this rotation operator, the rotation operator that takes the z-axis to the n-axis, that this is equal to spin up along that axis.
I have a question.
Yes, sir.
You have D dagger VD, but then on the next line
Yeah.
you have.
Yet, I know, because this one is active and this one is passive. And that was my little nod, right? If I have some coordinate system, x, y, and I take the vector v and I actively rotate it, I do it the other way on the coordinate system to do a passive rotation. You have to go back and remind yourselves. That's why the daggers appear on different sides. And it's always confusing. Am I talking about an active rotation on the vector or a passive rotation on the coordinates? That's why the dagger appears here. Thank you for emphasizing that, because I kind of slept over it. So now I ask you all, with my lovely handwriting here, if you can read it, can you see that this guy is an eigenvector of sigma sub n with eigenvalue +1? Yes, because I apply this to this. Then what it's going to do is, first it gives me, that gives me an identity. Sigma z on that is +1, and then I rotate it back. So indeed, this is an eigenvector of that with eigenvalue +1. Okay, so I can apply this rotation operator, which rotates the vector to the spin. And it takes spin up along z to spin up along n. Okay? Right. So, what we were discussing at the end of the last lecture is how we can use this to write spin up along this direction as a quantum superposition of spin up along z and spin down along z. Because spin up along z and spin down along z together form a basis. So any state in Hilbert space, pure state, can be expressed as a superposition of those. And we can see that through this rotation. So in particular, this rotation, I can obtain by taking this vector z, rotating it around the y-axis by an angle theta, and then doing an azimuthal rotation around the z-axis by phi, right? So I first put it on the cone, and then I sweep it around the cone to get it in the right place in the xy plane. So this is equal to, first I rotate around the y-axis by phi, and then I do an azimuthal rotation around the z-axis by an angle phi. Okay? So, how do we write down those matrices? So let us do a little aside over here and remind ourselves that if I have any, so now we're going to look at the case where J is the spin 1/2, which is h bar sigma over 2, right? So that for an arbitrary axis and an arbitrary angle, this is equal to e to the minus I theta sigma sub a over 2. This is a unitary matrix in 2D. It is a matrix in the group U2. Not my favorite band from the 80s, but a matrix of that sort. But it's special because it has a determinant 1. Because the two eigenvalues are, since this is +1 and -1, the eigenvalues are e to the plus or minus I something. You multiply those together, you get 1. So this is in the group SU2. Okay. And one of the special things about these matrices, besides the fact that they're determinant 1, is, as you know, we can write this, and this is only true for spin 1/2. It's not true for arbitrary J. It would be nice if it was, but it ain't. As
it would be indeed really nice if we were the case for it arbitrary.
that would be nice, wouldn't it? It ain't. Of course, for every kind of Pauli group, it would be true, but yeah, we will go back. Right. So, of course, we kind of knew this in a different way because any 2x2 matrix can be expressed as a linear combination of the identity and the three Paulis. This is that representation. If I wanted to, I could take the trace of this matrix, right, and the trace overlap with the three components. I'd find that's another way of getting at this expansion. It's typically done with a Taylor series expansion and using the fact that the Pauli squared in the identity. But there are other routes to get to that place, okay? If you don't have this formula in your mind, put it there and keep it. You use it all the time. So this is true for only SU2. All right, so let's look at this matrix, or operator. We have sigma sub z, so this is equal to e to the minus I phi over 2 sigma z, e to the minus I theta over 2 sigma y. Right? That's what that is. Don't forget your over 2. That rotation angle is that, but the over 2 is because this is physics and it was spin 1/2. Well, it's math too, but anyway. then is equal to, so let's write this matrix in a representation as a product of matrices in the Z basis, the standard basis. This matrix is easy to write down in the standard basis because it's diagonal in that basis, right? And so what does that matrix look like in the standard basis? Yeah, so it's diagonal, first of all. And it's an either the plus or minus diagonal. Which one has got the plus and which one's got the minus? Assuming I order the basis that I have first up and then down. So the eigenvalue of this is +1 for spin up. So it's either the minus I up here and either the plus somewhere down there. Okay, in the standard basis, ordered in the standard way. What about this matrix? Well, that matrix is equal to cosine theta over 2, see from this guy, that's the identity, minus I sine theta over 2 times sigma y. And what does sigma y look like? Well, it's got the zeros here, it's got the minus I here and the minus I there, right? So this matrix is cos theta over 2 sine theta over 2 minus sine theta over 2 cos theta over 2. Right, so with that said, if I want to write spin up along n represented in the standard basis, okay, one way to do it. Maybe, you know, there are many ways to skin this fish. So, what do I got? I have e to the minus I phi over 2 cos theta over 2 and e to the yeah, and e to the I theta over 2 sine, let's say theta and then e phi. So I'm going to factor this out and write this as cos factoring that out. So let me write this a little more clearly. That means that up along n is equal to that. And typically the phase convention we do, since it doesn't matter what the overall phase of the state is, we just have to choose some convention. And the typical convention we choose is to take that phase up there to make this one. That we just choose the phase convention and this is true. Yes, sir?
There's some homework problem that says you can make some SU2 arbitrary out of some phase plates, but in that case, you can't throw out the overall phase, because the SU2 requires that you're determining as one.
Well, there's two different issues of the overall phase. There's the overall phase of the state and the overall phase in the definition of the unitaries, okay? So any matrix of this form is SU2. If I have anything else in there, if I have some overall, because of course, if I have something here which is e to the I gamma times the identity matrix, that's still unitary. But that's not SU2,
Yeah,
that's U2.
right.
So I don't want to get into answering homework questions here in class. We'll come back to those in office hours. But we'll have to think about the relevance of that to the particular problem. So let's come back to that in another time. Okay, but importantly, this is our typical convention for these states. We say spin up along N is this, and spin down along N by the same arguments would then be the following. I want to get the convention correct because I think I'm going to screw it up. Yes, that's right. So these are two orthogonal vectors, and they are obtained with an appropriate overall phase by a rotation that takes the z-axis to that direction in three-dimensional space. Okay?
Professor, for that bottom line,
Yes.
of Z on the sine theta over 2 term.
Yes. Hold on a second. Yeah.
Just to add to this question about the global phase,
Yes.
do you think of the state as I don't like to say, a vehicle to calculate probabilities of measurement outcomes? Those probabilities are not going to change regardless of what is the value of the global phase. So you can as well ignore it.
That is, of course, true. I mean, I think the detailed question of what happens with the wave plates in the homework, we'll come back to that. All right, so let's take a good look at these. This particular, this one is something, again, you should kind of memorize. It tells me if I have a spin that is pointing along some direction in physical space, and that direction in physical space is parameterized by the standard polar angles that are drawn so beautifully here as theta and phi, then I can always write a spin along that direction as a superposition of spin up and spin down weighted by these probability amplitudes. Okay? So for example, if I wanted to say what is spin up along the x-axis, what are theta and phi?
Theta's pi over 2.
So example, let's say that E sub n is the x-axis. Of course, I just erased my beautiful sphere. try again. Oops. Okay, so that's the y-axis, and that's the x-axis, and that's the z-axis. So along the x-axis, what is theta and what is phi? Theta is pi over 2, and phi is 0. Therefore, what is, according to this formula, what is spin up along x? Cosine pi over 4, which is 1 over root 2, spin up along x, plus 1 over root 2, spin down along x. Which of course we know. Z, we mean z, which of course we know. Yes, we know that. Okay? Spin down along z, along x. It's not. Put that. Put a spoon back in my pocket. All right. Now it's all perfect. All right. Spin down along x. So in that case, this is equivalent to the spin along the minus x-axis, right? So spin down along x is spin up along minus x. One way to think about it. And that, in that case, what do we got? Well, again, we have theta is pi over 2, but phi is pi. That is the minus x-axis. That is spin up along the minus x direction, which is spin down along that direction. Which is then what? Well, we got the same cosine and sines, but then we got e to I pi, so we got the minus sign. Right? The y-axis. In this case, theta is pi over 2, but phi is pi over 2. In which case, spin up along y is 1 over root 2, spin up along z, plus I, 1 over root 2, spin down along z. And spin up, and then if I have the minus y-axis, spin up along minus y, which is the same thing as spin down along y, is then equal to that superposition. Clear? All right. So, what we now have just shown, of course, is that we can express the spin up along any direction in space as a particular superposition of spin up and spin down along the z-axis, parameterized by the directions in physical space associated with that spin. The converse, or the inverse, or some of the other one is also true, which is to say, any pure state in the two-dimensional Hilbert space is spin up along some direction. That's all there is. There's only spin along some direction when we're talking about a two-dimensional Hilbert space. How can we see that? Well, if this is some state in the Hilbert space, it can always be expressed as a superposition of spin up and spin down along Z, right? Because any state in Hilbert space can always be expressed in terms of the basis vectors, and these are the basis vectors. If it's normalized, then this is true. Right? So, anybody have a suggestion? I want to ask, what is the direction? I claim that this is equal to, up to some overall phase, it's equivalent to, by the Manuel rule, spin up along some direction. And this direction is characterized by polar angles theta and phi. I ask you now, what are the directions theta and phi that this corresponds to? Given an alpha and beta, what are these guys? Well, I can just say, I'm just going to define this to be cosine theta over 2, and this to be sine theta over 2. That's consistent with this equation, because sine squared plus cosine squared is 1. Right? So, given this, I can always, for whatever this magnitude of that probability amplitude, or said another way, the theta here is equal to twice the arctan of absolute beta over absolute alpha. One way I can write it. Right? Because the tangent of the ratio is that. Okay. What about the angle phi?
We just have to make a global space out.
Yep, exactly. So I can write as, because we're suggesting, I'll say factor that out. Right? So this is the, I've written in polar form, the complex number as having a magnitude and a phase. The phase is the arg of the complex number, right? Everyone agree that those two things are equal? And so what should I choose for phi?
Twice the argument of beta minus.
Actually, it's not, that one's just even no 2, because it's just phi. Yeah. So, that was a trick question. So the relative phase between spin up and spin down determines the direction phi, and the relative amplitude determines the angle theta. So the angle theta is determined by the relative amplitude of spin up versus spin down through this trigonometry. And the relative phase in the probability amplitudes determines the direction, azimuthal direction phi of the spin. Okay? So, given a spin, there exists a direction, or given a pure state, of this spin 1/2 particle, it must itself be spin up along some direction. And that direction in physical space, this is not a direction in Hilbert space. This is a direction in physical space of a physical spin. That direction of a physical spin can be found in terms of the relative amplitude and relative phase of those two probability amplitudes. Okay? Now, like it gets even more confusing. Since we just said that any pure state is associated with a direction in space, these directions in space also is the Hilbert space. This is the geometry of the Hilbert space of a spin 1/2 particle. It is a sphere. It is called the Bloch sphere. So let's review that. I can make this more precise, and we'll come back to that, and I don't have to keep saying this up to overall phase in a more precise way in a moment. Okay? That's what we just showed here. Okay? So how are we going to find that direction? So we define the Bloch vector as a vector in three-dimensional space. And given a state, I define the Bloch vector as the expectation value of the vector of Pauli matrices. This vector, Q, thus has an x component, a y component, and a z component. Okay, is that clear? This, typically in old-fashioned AMO physics or atomic physics is called, these components are typically called U, V, and double V. Although we don't use those so much anymore, we will, because that's how Bloch did it. Okay. Now, it is an exercise of the reader. Didn't want to give you too much homework, but now I will, kind of on the side. It won't be graded. For you to prove the following: that when, for this case, of course, psi itself is equivalent to spin up along some direction, right? So I claim that if I look at the expected value of the Paulis with respect to that state, what do you think I get for that particular state, spin along that direction? What vector is that?
Q.
Yeah, it's Q, which is equal to y in terms of this thing. What is Q equal to?
sigma sub n?
Sigma sub n is a matrix. This is the expectation value, so it has an x component, a y component, and a b component, x, y, and z component. It's a vector in 3D space, this vector Q. And I claim that this vector is the direction in space. Prove it for yourself. How would you prove it? Any thoughts?
Just write the Pauli vector in terms of the E sub n, and then fixing orthogonal.
That's right. So there's lots of different ways. I can just take this expectation value for E. We know what the sigma of the Pauli X matrix is. We know what the Pauli Y matrix is. We know what the Pauli Z matrix is. And the state is the state which has a column, it's a column vector, which has a spin up component, spin down component, and just take those expectation values. Or you could be more clever. Yeah.
You could think of the expectation value as trace of sigma times the density operator of n. And then it means it would be the vector.
But you're using something that you know. You're sort of assuming the solution, which is, of course, that is.
So you can insert to rotation in Dagger and rotate the basis, yeah?
Yeah, you can do rotation, you can do all kinds of stuff like that. Yeah, Ben, you had.
So that it works for Z to clarify symmetry, that it works for
Yeah,
everything
that's
else.
kind of like, yeah, it's similar to the rotation, but you need a little bit of like 3 steps more, maybe 2. But yeah. All right. So, what this says is that I can map. So now I want to come to what Vika said, because I want to really clarify this about what I mean by the iterative. It's really what we call projective Hilbert space, because we've gotten rid of the phase. So, I want to talk about the space of quantum states. My quantum state, what's a quantum state? A quantum state is a density operator. Okay? Now, we're restricting ourselves to a spin 1/2 or 2D Hilbert space. Every such operator can be expressed as some amount of the identity and some amount of sigma x and some amount of sigma y and some amount of sigma z. Because we said at the beginning of this lecture that any 2x2 matrix can be expressed as a linear combination of the Paulis and the identity. So this is equal to the trace of rho times the identity over 2 plus the trace of rho with the vector of Paulis dotted into the Paulis over 2. Does everyone agree with that statement? We had the little a0 and the a vector. This is the little a0, and this was the a vector when this was the operator a. Now it's the operator rho. Rho can always be decomposed into some amount of identity, some amount of sigma x, some amount of sigma y, and some amount of sigma z. And this is the rule. What is this if this is normalized? 1. So, therefore, rho is equal to 1/2 the identity plus a vector q dotted into sigma, where q is equal to the expected value of sigma, which is the trace of sigma with rho. Because we remember everything that I say, that the expected value of an observable we obtain by taking the trace of that observable with the state. This is the generalization of what I wrote down here. But now, for an arbitrary state, pure, mixed, or otherwise. So, this is to say that every quantum state is in one-to-one correspondence with a vector in 3D space. It's an amazing but confusing to some, takes a little while to get it, geometric fact. So, that is to say, I can draw this sphere there's a vector q on the surface of the sphere. For a pure state, as I challenge you to show, q is a unit vector along some direction. And therefore, it is a vector which has magnitude 1. It lies on the surface of the unit sphere. A sphere which has unit length, and then it's got these directions. This is the x-axis, this is the y-axis, this is the z-axis. This direction is the direction which is equivalent to spin up along n. So spin up along n is that direction on the sphere. But it's also a quantum state. Now, pay attention. There is a difference in the geometry. The different there's a notion of orthogonality. What vectors are perpendicular to one another in physical space? But that's not the same as what is perpendicular to one another in Hilbert space. It is not. What direction, this is spin up along Z. What direction in Hilbert space is the orthogonal vector? Spin down. The north pole is this. The orthogonal direction is the south pole. So you shouldn't think about this, the geometry of the space, that it inherits the geometry of 3D space. It has a different geometry of Hilbert space. Nonetheless, it's the same set. So, what is the orthogonal state to this state in Hilbert space? Down along n, which is that guy. Antipodal states are orthogonal. Spin up along x is here, and spin down along x is there. Spin up along y is here, spin down along y is there. These two states, spin up along x and spin up along y, are they perpendicular in Hilbert space? No. There is a finite overlap in Hilbert space between them. All right. Come back to that in a moment. Now, what about for the mixed states? So, oh, by the way, I said this before, but I'll say it again. This is called the Bloch sphere. This unit sphere is called the Bloch sphere, one of the most useful modern constructs in quantum mechanics. It's old, but It's only more recently come to the fore when people start to think about quantum information. Notice, okay, maybe I should draw this over here because it's potentially interesting. It doesn't matter whether I'm talking about a spin or any qubit. I can have a Bloch sphere for any qubit. So for any qubit, the north pole is 0 and the south pole is 1, because that's the way in which I define what's called the logical or the computational basis. So then, I ask you, what's the state that sits over here? What superposition of 0 and 1 sits right there on the Bloch sphere, which is the so-called x-axis? Yeah, it's spin up along x, which you said was the superposition 0 plus 1 over root 2. That's up along x, right? And what state sits over here?
0 plus I, 1.
Exactly. And what state sits over here? Well, cosine theta over 2, 0 plus e to the I phi sine phi over 2, 1. Where those are the polar angles. Theta and phi. So, in our homework, we got polarization states of light, where this is, say, horizontal polarized, and that's vertical polarized. Notice that horizontal and vertical are not perpendicular to one another on this sphere. They're antipodal states. Well, actually, we had right or left, or maybe we chose the right and left circularly polarized light. That's the typical way you would do it. And then this was horizontal, and this was vertical on this side of the sphere, etc. This sphere has another name, because it was, this is a nice structure, and people who were smart discovered it over and over again, and good old Poincaré discovered this long ago in the context of thinking about polarization states of light, and the Bloch sphere in optics is known as the Poincaré sphere. It's the same thing. It's exactly the same mathematical structure, except instead of thinking about spins, you think about polarization. But they are isomorphic. You just map one onto the other. Great. Mixed states. Oh, before I want to say that, I wanted to say for pure state, a pure state is spin up along some direction. Which is equal to 1 plus the Bloch vector dotted into the matrix over 2, right? That's what we have over here. Right? Which is what we call 1 plus sigma sub n. So this is a very useful mathematical identity, a way of writing a projection operator onto a direction of Hilbert space in terms of locality matrices. For example, up along Z, is equal to the identity plus sigma z over 2. That's, you can kind of see that in your head by thinking about the matrices. In the matrix representation, this is that guy, the guy that just had a 1 on the diagonal. And this is equal to a half, 1, 1, plus 1 minus 1. Add them together, you get that. If I had spin down along z, I'd put a minus there. And then I would get this, the projectional. So that's a useful trickaroonie. Okay. Before I get to that, before I get to the mid-state business, let's look at the following thing. So I just did my little drama queen thing about how directions on the sphere are not the same as the directions as far as orthogonality goes. Okay? I mean, this is the physical direction of a spin that I would rotate. It's also related to a quantum state, which has a certain associated direction. But the inner product on Hilbert space is not the same as the inner product on R3. So now I ask you the following question. Suppose I have 2 states, pure states, and I want to look at the overlap in Hilbert space between a spin along n and a spin along n prime. If I want to calculate that, there's lots of ways to do it. But here's one cute trick. I'm going to play the trick of using the relationship between the trace between matrices and the inner product. Okay? So let me write this as the trace Everyone agree that those 2 things are equal? How do you know? How would you prove that? So this is the inner product between these guys. And then I got to take the trace. How do I take the trace? You get it exactly. I didn't hear the sound, but now we did. Okay? And everyone see that this equals this. This is the trace inner product of 2 states, rho prime and rho, where one of them is the state associated with this direction, and the other is the state. It's a kind of sometimes what we call the fidelity for pure states. That's just a little word to the wise. All right, but how am I going to take that trace? Any thoughts? I'm listening. I'm not looking because no one wants to.
Then I go in terms of the body.
Exactly, super. All right, Shiva, I agree. That's a good idea. That's a trace, not a T. So, as was suggested, let's write the block vector representation of each one of these guys. So this is equal to the trace of the identity plus E sub n prime dotted into the Pauli's over 2, and 1 plus E sub n dotted into the Pauli's over 2. Okay? So, what is that equal to? So that's equal to the trace of, I'm going to bring out the factor of the 4 out here. The trace of the identity plus En plus En prime dotted into sigma. Plus En dotted into sigma and E prime dotted into sigma. Those are the 4 terms, right? Do you agree with that? Okay, trace of the identity is equal to 2. Trace of this thing, 0. Why is that? Because all the Pauli matrices have trace 0. So it's 3 different components. There's going to be a sigma x, there's going to be a sigma y, there's going to be a sigma z. Take the trace of any of that, that's 0. What about this last one? Oh boy, now here we get tricky. Lots of ways to do it, but the best way to do it is to exercise your power of Einstein index notation and repeated indices. And to remember that, so So what have I done? What I have done is to decompose this vector into its components. It has components I and components j, and these are its unit vectors. Repeated indices, right? So this repeated with this would be the vector sigma. And this repeated with this is the vector sigma. I just took out the components. Okay? Ooh, is that tricky? So what is this trace? Right? It's only the part, remember that sigma I times sigma j was I epsilon ij k sigma k. The trace of that is 0 plus delta ij times the identity, and the trace of the identity is 2. So this is 2 delta ij. And so when putting it all together, what I get is that this is equal to 1/2 1 plus, this is so beautiful. I love this. So, what this says is exactly what we were saying before. The dot product between the vectors in Hilbert space, the bracket, is not the same as the dot product here, but it's related. In fact, if I have some angle, so let's say that the 2 vectors in physical space, the direction En and En prime, has some angle between them. And therefore, the dot product is the cosine of the angle between those 2 vectors. Then, the inner product, the square of that is 1 plus cosine theta over 2. Which, if you remember, or if you don't, I'll tell you, is equal to cosine squared of the half angle. This you should memorize. There's so many things to memorize. But you should. You should know that. You should know that if I have two spins that are pointed in two different directions and I want to know what their inner product, the inner product square, the probability, is the cosine of the half angle. So if they are on opposite sides of the pole, then one of these is like this and the other is like that. Those are orthogonal directions in Hilbert space, because the angle is pi. And in Hilbert space, it's half that, pi over 2, which would be 0. That's a very important fact. All right, I want to conclude quickly by just saying one or two words here about mixed states. So, for a mixed state, we know that the trace of rho squared is less than 1, right? In fact, with the same kind of trickery that I just did, now for these guys, this is going to be equal to 1 plus the magnitude of q squared over 2. I am using exactly the same trick that I used before. This is and what's the minimum value this can be? Trace of rho squared. 1 over the dimension, which is 2 in this case. So now I ask you, how does the magnitude of the block vector go between pure and mixed? Well, we just said for the pure state, the magnitude of q was 1, and that means the trace of rho squared is 1. What's the minimum value of q? 0. This is always confusing. The purity goes to 1 over d, but the magnitude of this is for completely mixed. So to conclude, what we have is the following. The block sphere becomes what's called the block ball, although most people don't use that term. They just call the whole thing the block sphere. Meaning the surface of the sphere, the place where the unit vector, where the block vector has unit magnitude, are the pure states. The interior of the sphere are the mixed states. And the degree of mixedness, as measured by the purity, is related to the length of the block vector. The origin of the block sphere is where q equals 0. When q equals 0, what is the state? The state is this. That is the completely mixed state. This state has no coherence. Remember, it has no off-diagonal elements in any basis. It is the most unpolarized state. It is a 50-50 statistical mixture of anything. The states that are partially mixed are interior to the sphere, but not quite with the same magnitude. And on the Poincare sphere, we would say these are the fully polarized states of light. The middle of the sphere is completely unpolarized light, and in the middle is partially polarized. It's all the same thing. This is a beautiful geometry. It really is. It's very, very, very important geometry that you really need to ingrain if you don't have experience with it in thinking about quantum mechanics. Because the most basic quantum mechanics we think about is just two states, the quantum bit, and it's all encapsulated in the geometry of the block sphere. All right? Very good. I'm gonna go have my yogurt. See you later.